Thank you very much, Nazard, for the very kind introduction. It's really cool to see a standing room only crowd, considering that this is the shortest distance that I've ever had to travel for a seminar. I thought I would pick a really specific title, and this is for a reason. I want to be able to highlight the contributions of many former and current group members, and the only way really to do this is by being as general as possible, because our group works on a number of different things. But they all kind of have this common theme, this common scientific problem of nanostructured and organic thin films that give rise to electrical and mechanical properties that are then useful in a variety of applications. I hope to convince you by the end that there is at least some commonality here. So we work a lot with conjugated polymers. Conjugated polymers are semiconducting polymers. They have a bonding arrangement of single bonds alternating with double bonds, and that gives rise to semiconducting behavior. Solar cells made from these materials can be up to 17% efficient. Actually, they've been incorporated into perovskite solar cells recently, where they're more than 19% efficient, and the charge transport properties in terms of field effect mobility can actually be better than some common inorganic materials like amorphous silicon. However, there is a problem. These are some roll-to-roll printed solar cells made by a group that we collaborate with in Denmark. And what this group did was deploy these solar cells out into rural Zambia as part of the United Nations Lighting Africa initiative. And what the researchers found when they got the cells back from the field test is that they had significant signs of mechanical damage, way worse than the photochemical damage that you would expect based on organic media. Around the same time that I started my group here, the NSF and Office of Navy Research sponsored a workshop that asked the question, do organic cells fracture cohesively or at interfaces, and what's been done to prevent these cells from failing mechanically. So the near-term goal is to address this problem, because organic semiconductors are becoming ubiquitous in everyday life. So OLEDs, they're not based on polymers yet, but organic electronics in general are becoming quite a significant commercial interest, and we don't want them to fail thermally and mechanically. So this is the near-term goal. The longer-term goal is to enable something like this. This is Lieutenant Commander data from Star Trek: The Next Generation. And when I started working on the biomedical side of things, my work was covered in the NIH Director's blog. And I mentioned to the reporter that I was inspired by Star Trek: The Next Generation, particularly data, because I imagined that he had organic electronic skin that had good charge transport, self-healing, mechanical toughness, and so on. And then Brent Spiner, the actor who plays Data, tweeted that story to 4.5 million followers, and that was the happiest day of my professional career. But the problem is, if you look down into Data's skin as you stretch it, you'll notice all these microscopic cracks, and that's because, literally, this is an AFM of Data's skin. You look down into there, and there will be these microscopic cracks. So the goal is to be able to use molecular engineering and microstructural engineering in order to mitigate this problem. We are also interested in the capacity for self-repair, biodegradability, multimodal sensitivity, and also a new area for us, actuation for tactile response. So we're really interested in incorporating aspects of biological materials into these organic electronic materials. Now, mechanical properties of polymers have been studied for a long time. And why not just take everything that's known about the mechanical properties of engineering plastics and commodity polymers and just translate all of that research into pi-conjugated or semiconducting polymers? And the reason we can't do that is summarized by just looking at the structures. So this is PTB7, and this is polystyrene. You'll notice that PTB7 has these alkyl side chains that serve to increase the solution phase entropy relative to the undissolved state, so you can process these materials from solution. We also have rigid backbones, low degrees of polymerization, high dispersities, large monomer residues. So if we were pharmaceutical chemists, this might actually be like the size of a drug molecule, but this is just one monomer residue. Small quantities available, especially if we're doing a pilot scale synthesis. We might only make 100 milligrams, which we could only use to spin coat a few films. We can only make thin films. If you look at the microstructure and morphology, you have a range of microstructures available. You can have interdigitation of these side chains. You can have non-spherulitic morphologies. You can have intercalation of small molecules between the side chains. You can have weak glass transition signals, and they are quite challenging to model. Critically, a problem we have with semiconducting polymers that we don't have with polystyrene is that we have to be able to retain the charge transport properties when these materials are formed. So if you just look at a classic example of a conjugated polymer, this is poly-3-hexylthiophene, the fruit fly of this class of materials, and you stretch it out as a function of increasing molecular weight, you can see here that the extensibility and toughness, it's the area under this curve, increases as a function of molecular weight. And that makes sense because as the chains get longer, the more physical entanglements there are. And you can calculate the number of entanglements using, in this case, a coarse-grained molecular dynamics simulation that my former student Sam Root did. And this basically shows that the number of entanglements goes up by approximately a factor of 6 as you go from 15 to 80 kilodaltons. This experimental work was done by Daniel Rodriguez, who's now an engineer at Cymer ASML. Now, the molecular weight is something that polymer engineers have been manipulating for a long time to change this or that property. But what about an aspect of the molecular structure? So let's look at the side chain. As you increase the length of the side chain, the tensile modulus goes down and drops off between C6 and C7 and then remains relatively flat. Now, what's going on here? Is there something magical about C7? Not really. It's really something magical about where you have the thermostat set in the lab, because that's where the glass transition drops from above room temperature to below room temperature, with C6 being about at the borderline. But even with this one little knob that we can tune, this one carbon homologation, it's called, of the side chain, from C6 to C7 to C8, we can actually have a profound effect on the electronic and mechanical properties. So if you look in this middle column, or in the left column, we have good charge transport properties for C6, but good thermal and mechanical properties for C8. So C7 is kind of the best of both worlds here. We kind of combine halfway decent properties in both electronic and mechanical function. Even doing that, we can do some things with solar cells that you can't really do with a glassier material. Like you can make a solar cell and stretch it out and then bond it to hemispherical surfaces. You can also make solar-powered wearable devices. So this is a device that is on a 10-micron piece of polyimide tape, and you can bend it to a radius of curvature of about 100 microns 1,000 times, and it still is enough to power this watch. And it says 1201 and not 12, so that you know it's been working outdoors unencapsulated for at least 1 minute. That was key for us. This device here is an all-rubber solar cell, so the substrate, the encapsulant, the anode, the cathode, and the N and P-type materials are all low-TG elastomers. So possibly the first all-rubber semiconductor device in the literature. And this work was done by Tim O'Connor, who is a graduate of my group, also happens to be at Cymer ASML. Given the importance of the glass transition in determining the mechanical properties, you might think that it was fairly easy to measure. And it turns out that because these materials have these side chains that are already liquid-like at ambient conditions, it turns out you don't get a huge change in heat capacity when you surpass the TG of the main chains. So actually what happens is that the signal that you get calorimetrically is very small. So where's the TG? So given this problem, my students Sam and Mohammed came up with a technique to measure it spectroscopically. So the hypothesis is that because you have these photoactive pi-conjugated units, if you supply enough activation energy into the system, they should be able to line up in the pi stacking direction and give you an aggregate absorption by UV vis that's indicative of this ordering. And once you surpass that thermal barrier, we hypothesize that that should be around the glass transition temperature. So if we bring these materials to a certain temperature on a hot plate, we remove it and measure a UV vis spectrum, then we calculate a deviation metric, which is the sum of the squares of the differences in absorbance from room temperature to a temperature of interest. And what we get is a series of these UV vis plots where all of the action is happening right here. This is where the aggregate absorption is popping up. And if you plot these this deviation metric, then the part of the plot where it changes slope should be around the glass transition temperature. And it turns out that that it is quite close. So this technique works for materials that form these pi-stacked aggregates, but it doesn't work for amorphous materials, and it doesn't work for materials that form or that have order along a different crystallographic axis. So, for example, if the molecules stack like this, there's no real difference in the absorption. So it works for a number of materials, but not others. We were interested in looking at the photovoltaic properties and mechanical properties for a large number of these types of polymers. So we collaborated again with Frederick Krebs, who at one point hired like 10 synthetic chemists to make 100 compounds, which are basically these acceptor units crossed with these donor units. So these are electron withdrawing groups, these are electron donating groups, and when you add them together, the linear combination of molecular orbitals causes a shrinkening of the is that a word, of the band gap, and therefore a low band gap material. So this is a plot of the tensile modulus. These values are measured by us, and at this point we were considering the green values, so low values of the modulus, to be good for deformability and for wearable sensors and that kind of thing. This is a measure of the crack onset strain. So if you put the film on an elastomer and you stretch it out, these are the strains where the cracks first appear, and the higher, the greener, the better. If you take these metrics and you take 1 over the tensile modulus times the crack onset strain, and this is arbitrarily defined coefficients of 1 to 1. Who knows if this is the best way to do it? But if you multiply this by the power conversion efficiency, as in a solar cell, and you divide that number by the number that you get for P3HT, the fruit fly, in the literature, then you can see that there are a number of entries in this table that are actually better than P3HT. So this is kind of a brute force combinatorial way of doing this, but we can see that there is light. Some of these actually do behave much better than P3HT. This work was done by Suchil Savagatrap, who is now a professor in the Chemical and Environmental Engineering Department at University of Arizona. He did his postdoc with Tim Swager at MIT after finishing in my group. So from this kind of brute force experiment, we expect to be able to define some design rules. So isolated rings along the backbone tend to give you more deformability than fused rings, and branched side chains give you more deformability than linear side chains. But we kind of knew that before doing all of this. It sort of just makes sense. So why can't, can we develop a deeper, more sophisticated picture of what's going on with these materials? So we chose 3 materials, not because they're particularly well performing, but because a lot is known about them in the literature. So these are the structures of those materials. And we chose them because a lot is known, but also because they occupy a range of morphological behavior. So PDT-STPD is semicrystalline, PTB7 is intermediate, and TQ1 is amorphous. So my student Sam, who's now a postdoc with my old advisor at Harvard, did fully atomistic molecular dynamics simulations of 60 chains of 12 repeat units each in both a neat film and a bulk heterojunction. Now, a bulk heterojunction is a PN is a distributed PN junction where your P-type material is this polymer and your N-type material is C70 fullerene that has some stuff on it that makes it more soluble. So there are 2 types of morphologies generated. There was a melt-quenched morphology and a self-aggregated morphology. you can kind of think of this as sort of the thermodynamic morphology, where you start out with a melt and then you cool it down to give you a high density film. And the self-aggregated morphology is like what you might get if you put the polymer in a bad solvent, and the polymer scrunches up to interact better with itself, but then when you solidify the film, you leave lots of void space and you don't maximize the number of entanglements with the other molecules in the solid. So the final structure depends on the solution conformation, and using a paradigm developed in the early 2000s and then developed further by Nick Jackson as a member of Mark Ratner's group, we categorized, or Sam categorized, the conformations into these four conformational classes: globule, toroidal, folded, and extended. And what you can do is take a snapshot of these of the solution phase material, and then you can calculate the number or the fraction of extended, folded, toroidal, and globular. And if you just take a look at just one entry in this table, the red bar here, which corresponds to TQ1, is mostly globular, and that doesn't offend our intuition because that's the one that's amorphous. So it should have the least kind of order. What was interesting from this computational experiment is this oscillatory tangent correlation function. Now, normally with a conventional polymer like a polyolefin, like polystyrene, you expect no correlation, or you expect the correlation to die off. So if you take a unit vector from each monomer residue and you take the dot product as you go along the chain, you expect that the correlation would just decay exponentially. But we don't see that behavior. We see this oscillation. So that means that there's some amount of helicity that's being introduced into the material, in part because the backbone of the chain has these ladder-like or ribbon-like character of all these fused rings. So it behaves a little bit like a ribbon as opposed to a string. One thing that's really useful that the simulations allowed us to do was to calculate the density of entanglements. An entanglement is a topological feature in a polymer film that has to do with the fact that polymer chains can slide past each other, but they can't pass through each other. So it's almost like a link in a chain. And how you can calculate this is you take the intersections of the primitive paths of these polymer chains, and each intersection is a kink, and that's proportional to the number of entanglements. If you plot the stress-strain behavior for these materials between 0 and 3% strain, so still a low strain regime, what you can see is that the way in which you process the film has a lot more influence on the modulus of the film than the identity of the molecular structure. So the molecular structure this model predicts would be important insofar as it affects the solubility and the kinetics of solidification, but actually the way in which the film is processed has a huge effect. So actually, these materials are pretty much indistinguishable by mechanical properties. The only thing that's different is that they're processed in a different way. So from the very small scale of looking at models of these polymers, we were also interested in their behavior in whole modules. So these devices were fabricated by the group in Denmark. Actually, these are the only cells in the talk, the only devices in the talk that weren't fabricated by us, just because they happen to have the roll-to-roll processing capabilities in their lab. And we, meaning Allects Zaretsky and Mickey Finn, made these solar cell torturing devices. And the goal here was to be able to predict, in order to mitigate where within the device stack these cells would ultimately degrade. And the good news is that some of the cells actually could survive for more than like 10,000 cycles, so much so that we just kind of had to stop collecting data. So here's Mickey, he's in the back, and he did this work. So we're interested also in in what's happening microscopically as you fatigue these films. So if you take these semiconductor films and you stretch them many, many times, it makes sense that that you would accumulate cracks and defects. For example, if you have a Tic Tac box and you take the lid and you bend it over like 100 times, eventually the lid will break off the Tic Tac box because you're accumulating bond scissions, and ultimately the film or the material will be fatigued. So that's what we tried to do with semiconducting polymers. And we use the same sort of technique in using UV-vis spectroscopy to calculate the amount of degradation based on what happens to the aggregates in the solid films. So this is kind of like a little UFO-looking, another solar cell torturing apparatus that Andrew Chang, an undergrad in my group, monitored overnight through many thousands of cycles. And what happens is that the more you stretch the film, the more the aggregates are kind of pulled apart. Interestingly, what you also see is that after these films are stretched and brought back into equilibrium, they wrinkle. And the wrinkling wavelength will change depending on the number of times you stretch it. And the stiffer the film is, the longer the wrinkling wavelength is. So as we stretch the film, the buckling wavelength goes down, the wrinkling wavelength goes down, which means that we're making a less stiff, less aggregated, but actually substantially more brittle material. So the way I liken this, what I liken this to is when you have like Campbell's tomato soup, which I don't know if anyone, well, some of you may have had this experience, but you pour it into a bowl and you microwave it, and then when it comes out, if you let it wait too long, it forms a skin on the top. And that skin is both soft and brittle. So we don't normally think of things as being soft and brittle, but this material, once you fatigue it, is. This is Adam Prince, who did this work. He earned his PhD with us in 2015. Then he did his postdoc with Rainer Dausgaard at Stanford, and then he's now also an assistant professor at University of Arizona. Sometimes the cracks you get are useful. So usually in this field, when you stretch something and then it cracks, you say the device is dead. But actually the cracks could actually give you some diagnostic information as to the mechanical properties of the film. So this is some work done by Sam Mohammed and Kristan Hilby, who was an undergrad in the group at the time. And what they discovered is that the rate of growth of the aspect ratio of these diamond-shaped cracks can actually be related to the failure stress of the film. So that's kind of an interesting observation. So what you can actually do is if you plot the base 10 log of this rate of growth, it's actually related to the failure stress. So that's actually quite an interesting and useful idea that we've used in other places as well. So there's Mohammed and Kristan. They both happen to be PhD students at MIT. Mohammed in chemical engineering, Kristan in mechanical engineering, just started this past fall. All right, so we talked about computation, whole devices, whole films, but eventually we want to be able to control things on the molecular level. So what about chemically, what can we do? The goal here was to design a semiconducting polymer that had really lifelike properties. So not just mechanical toughness and stretchability like skin, but also the ability to biodegrade and even potentially self-heal. So this was a structure. I kind of drew something in a grant proposal that really couldn't be made, and then my visiting scholar and postdoc kind of redesigned the synthesis. This is what they came up with. This is a semiconducting segment, so you can see alternating single and double bond throughout the semiconducting segment. This here is a biodegradable elastomeric segment called polycaprolactone. And these materials had two different forms. One in which this aryl group is a single isolated thiophene group, and another where this aryl group is a fused thienothiophene group. So this material is going to be a little bit stiffer along the molecular backbone because it has a fused ring, and that's going to be, we think, important in another graphic from now. So if you take just the T version and you add and you have 75 weight% of the insulated polycaprolactone, you can see that the extensibility and toughness increases a lot. And you would expect that, that as we're increasing the extensibility and toughness by adding all of this insulator, that it would dilute the semiconducting behavior, and you would end up with just like junk at the end, right, that can't conduct any charge at all. Turns out that that's not what we see. It is what we see for the single thiophene unit, but for the polymer with the fused thiophene unit, actually the whole mobility as measured in a field effect transistor by Andrew Kleinschmidt retains its mobility even up to 90 weight% of the insulator. So what's going on there? It turns out that if you look at the UV vis spectra, the aggregation behavior is actually improving too. So these materials are actually forming better aggregates. And also, if you take this material, you compare the thiophene to the thiophene, and you hydrolyze all the PCl, leaving only the semiconducting segment behind. If you kind of convince yourself that these high aspect ratio structures form these percolated networks, then this is actually consistent with the fact that we have better aggregation and we also have consistent charge transport as we increase the amount of insulator. So we're actually making this better by adding more insulator, which is pretty cool. This work was done primarily by Fumitaka Sugiyama, who is a visiting scholar from Japanese synthetic rubber, and Andrew did the electronic characterization. This is some work that just came out in Chemistry of Materials on ASAP today. This is a project started by Sam and really finished and done by Rory, who did like 90% of the work to bring this to fruition. So basically, you take this material, you drop it in the back of this water bath, and then what happens is the solvent evaporates, the material solidifies, and you can draw it up on these rollers. Here are some photographs. The cool thing about this technique is that you can deposit it on significantly rough surfaces, and even surfaces that have pores. So if you try to spin coat or spray coat on a fabric, the material will bunch up, it won't be an even film, and you'll have holes in it. But if you solidify the film ahead of time and you draw it up, you can actually create this type of uniform film. So here's a film on textiles. You can make a solar cell. They're not very good solar cells yet, but you can make them. These are barrier films. So this is a conventional plastic, not a semiconducting material, that's deposited on a fabric, and the gas permeability goes way down once you have this thin barrier film. This work done by Rory, and then undergraduates Derek and Kartik, and grad student Allects. Okay, our interest in barrier films got one of my former students interested in graphene. He was interested in a number of different things. He just started in my group in 2012, and my group was new at the time, and he wanted to do graphene. And I thought, well, could there be a worse strategic decision for an assistant professor to do every project on graphene, because there were like 14 papers a day on graphene. So how do you differentiate yourself? That's the key to working in an area that's quite crowded. And I said, well, one of the things is that we can't spend $1,000 for a square inch of this stuff. We have to be able to find a way to make a lot of it. So he came up with this method where it's possible to recycle the copper growth substrate. So you grow graphene by CVD on copper, and then you usually etch the copper off, which gives you a horrible atom economy and yield if you're going to do this industrially. And what this process allows you to do is to transfer it to an arbitrary substrate. Allects, actually after he graduated, or actually while he was a grad student, started this company, Groltex, that is actually making this stuff commercially, so graphene and hexagonal boron nitride. But as a result of evaporating films onto graphene for the purposes of transferring the graphene, he discovered something interesting. So graphene is so thin that the surface energy of the substrate supporting the graphene can actually penetrate to some extent through the graphene. It can change its polarizability and therefore surface energy. So this phenomenon has been studied. It's quite controversial as to exactly what its origins are. It's called wetting transparency. It's been known for liquids for a few years, but this was the first time that we observed this phenomenon with an evaporated flux of metal atoms. So if you deposit, this is one evaporation of gold on the top, one evaporation of silver on the bottom. The only thing that's changing is the identity of the substrate supporting the graphene. And you can go from percolated morphologies to these well-faceted crystallites. In the case of silver, you can get these kind of globular morphologies that is kind of a function of the fact that silver has a fairly low surface tension. Metals have a high surface tension, but silver among metals has a fairly low surface energy, so you kind of get like silver forming rain-x on top of graphene on top of silver. Anyway, so some of these morphologies are actually quite interesting because they make these very small gaps and they have these kind of percolated, kind of nanoribbon-like structures, and you can tune these structures by tuning the material below the graphene. So some of the things that you can do, this is just showing that you can make a strain sensor. You can make quite a sensitive strain sensor because one, graphene is already piezo-resistive, and the metal actually has an effect of being able to tune the temperature coefficient of resistance so that you can have a near zero temperature coefficient of resistance. And also, the metal itself is piezo-resistive when it has small gaps, which could potentially be exploited. The tunneling phenomenon could potentially be exploited to make a very sensitive strain sensor. That's one hypothesis. Also, if you stretch out these thin metal films, you can get micro cracks and you can get increased scattering, which all have the effect of increasing the resistance with very small strains. So this is a small strain. This is about 10 part per million in strain that we can measure quite well above the noise. You can put it on the wrist and measure the pulse pressure waveform, and you can do this out to like 10% strain. Interestingly, you can also put rat cardiomyocytes on these sensors, and you can measure the contractions. So these are neonatal rat cardiomyocytes that are with the graphene, the silver or the nanoparticles butter side down. The cardiomyocytes really like the graphene, and you can measure the contraction forces with a very high resolution. So we're interested in this for potential applications in drug screening to do this in a 96-well plate format or above. Here is an example of how to use the metal and the graphene combined to combat thermal drift. So what the biggest problem with strain sensors, or one problem with strain sensors, is that if you walk outside and it's cold outside, the strain sensor will contract, and therefore it's also a temperature sensor. Also, the charge transport could be thermally activated in a material, or it could be hindered by high temperature. So you tend to also get temperature sensitivity along with strain sensitivity. But since metal has a positive temperature coefficient of resistance and graphene has a negative TCR, there's a sweet spot with a near zero TCR. It turns out that at about a nominal thickness of 10 nanometers with gold on graphene, you get a fairly flat response throughout this reasonable temperature regime. One of the things you can do if you have a sensor that's robust to environmental conditions is use it in various wearable on-body type systems. So we were contacted by a group including Eileen Shin and Kate Hutchinson at MD Anderson Cancer Center, and they were interested in studying the swallowing activity, monitoring the swallowing quality of head and neck cancer patients following radiation therapy. So after radiation therapy, there's a propensity for fibrosis to develop in the swallowing muscles. And the idea was if we can have an embedded strain and electromyography sensor, we should be able to monitor this activity over time in a non-invasive, unobtrusive format. So Julian, who's here, and Daniel went to MD Anderson and tested these devices on 7 dysphagic patients and 7 patients who had not yet exhibited dysphagia but did have radiation therapy. And what they found is that for one, it is possible to differentiate different swallowed boluses, so water, yogurt, cracker. It's also possible to use the combination of electromyography and strain information to differentiate head turning, take in, and swallowing events, so motion artifacts from the actual swallowing events that you're trying to measure. And actually, some of the features here correspond to distinct events in the video fluoroscopy. That is like a video X-ray measurement. So in collaboration with C.K. Cheng's group and ECE, it was possible to develop a machine learning algorithm that could actually classify these signals and predict with fairly good accuracy whether this was, for example, in this case, water, yogurt, or a cracker. This unknown signal. It was also possible to differentiate whether a patient had or was not clinically dysphagic. So ultimately, what we would like to be able to do is to take these types of medical devices and to put some kind of make a new paradigm of two-way communication with a clinician. So instead of putting these devices on the skin, what if there was some kind of mechanical scanner, like a CVS, and there was a patient who had some kind of swallowing dysfunction. They needed to see a speech pathologist that specialized in head and neck cancer. There might only be some limited number of people in a very few concentrated zip codes, but say this person lives in like northeastern Nevada. So what if there was a way to do a mechanical scan using some kind of robotic effector that could then be analyzed the way by hand, the way a radiologist analyzes an X-ray in the quiet of their office, which could be off-site. But that's not really possible using current haptic technologies. In fact, we're really interested in haptics more broadly. So haptics are the technology that interfaces with the sense of touch. If you've seen Ready Player One, that's a haptic suit that the dude is wearing. So we're interested in the sense of touch for a number of reasons. So human culture is kind of replete with artifacts that interact with all of the senses to convey information or to produce a thoughtful response. And these are well known in the visual arts and music, and taste and smell are often grouped together. But if you look at touch, it's kind of a big question mark. I mean, there's fabric, but fabric, which is designed to elicit a tactile sensation, but it's not really dynamic in the same way that a movie is or that music is. There's massage, but that's not a cultural artifact. That may be an aspect of culture, but it's not an artifact. There are massage chairs, which are cultural artifacts, but kind of suck. So the goal is to create a new interface between materials chemistry and touch, possibly for medical training, remote care, and maybe even something to do with tactile arts. Who knows? So the framework for our work is based on the idea of developing an RGB of touch which exists for vision. So right now this projector has red, green, and blue pixels in it, and it can simulate most visual objects using just 3 colors. And the goal is there some minimum number of tactile actuators? This is just a hypothesis, just a conceptual drawing, that would allow you to differentiate objects on the basis of touch. So on the basis of near surface properties. Now the reason we can't do this now is because haptic technologies today are extremely limited. So they're all most of them are based on a displacement paradigm, where something shakes like this when I'm about to run out of time is going to shake. This is a haptic device. Your phone or your Apple Watch have haptic devices in them, but they don't reproduce fine texture. They don't recapitulate anything that feels remotely like a real surface, much less the biological milieu, as you would need in a medical context. So we started, the hypothesis is that if we can have materials that can alter their physical and electronic and thermal properties in real time, then we should be able to recapitulate near surface properties and generate a much greater range of tactile sensations than are available to haptic devices that are just miniaturized versions of motors and speakers and electrodes and things. So we started off really simple, and the goal was, can we distinguish by touch hydrophilic and hydrophobic surfaces? So here's a silicon wafer that's been plasma oxidized, and here's one that's been silanized. And here's a contact angle to show you we did this right. We assiduously wash this one to get rid of all the physisorbed material, and then we do two types of psychophysical exploration. One where we slide our fingers, and then one of these three is not like the other. That's called the odd man out experiment, and then another we did just tapping. So it turns out that human participants are quite good at doing this in both the dry condition and the wet condition. That is, with these objects submerged, which could eliminate capillary forces, which could be a confounding effect. And also, we measured the effect of sweat or moisture content of the skin. So if you're giving a public talk like I am and your hands are sweating, you'd probably not be very good at doing this experiment. This work was done by Cody Carpenter, who just graduated and is now an MBA student. He graduated with his PhD, is now an MBA student at Wharton at University of Pennsylvania. Charles Dong, who is now an assistant professor at University of Delaware in the Materials Science Department. Nick Root, who is a graduate student who is now a postdoc in the Netherlands, who was working with V.S. Ramachandran. Okay. Just to show you, I didn't actually do any of this work. So V.S. Ramachandran is known for his work on synesthesia and treatments for psychophysical treatments for phantom limb pain. So when people have limbs amputated, they sometimes feel chronic pain, and he developed a mirror box treatment that for many patients can actually eliminate that pain. So you can do kind of cute stuff with this technique. If you pattern digital characters in the ASCII alphabet using 1 for oxidized and 0 for silanized, it's actually possible for human participants to read out letters with pretty good accuracy. Now, a good internet connection is something like 100 megabits per second, and humans can decode the ASCII alphabet at a rate of about 100 millibits per second. So we're not anywhere close to replacing digital storage with this technology. But anyway, you could read Lab. All right, in 4.5 minutes. Okay, so we were interested in kind of the mechanism for how this worked. So Charles created this surface force apparatus that he could drag across a surface that was either silanized or oxidized. And the hypothesis was that differential stick-slip friction behavior is actually what's responsible for the ability to differentiate. So you can imagine a few different scenarios. One in which the hydrophilic and hydrophobic surfaces give you the exact same stick-slip friction frequencies. Stick-slip is like when you open a creaking door. That sound is stick-slip friction, stick-slip friction instability being manifested. Same thing here. The other scenario is if they're totally different, you can have like totally different stick-slip friction amplitudes and frequencies and so on. So Charles did a cross-correlational analysis of this finger on a substrate at different loading forces and sliding velocities. So here's an example where these plots are pretty out of phase. These are quite different. Correlation has a lot of skew in it. This is an example with this different loading condition where there's a lot of similarity between, especially this trace here. So there's a lot of correlation. And then these are the results of an analytical model from a friction model from the 80s that kind of give you the same type of qualitative result. You can plot these data in an interesting way called a discriminability matrix. You just pay attention to this plot down here. We have the velocity here and the downward loading mass here. Now, areas where you have green and yellow are where discrimination is favored because the friction is totally uncorrelated or quite uncorrelated. And given these loading but interestingly, where it's red, the plots are pretty similar. So we can't predict how the surface is going to feel unless we consider the loading conditions as well. What's interesting about this result is that when human beings perform these discrimination tasks, they're not constructing these matrices. They're just kind of automatically homing in on the right combination of force and velocity that allows them to make the discrimination. Interestingly, when you add fingerprints, so topographic features to the surface force apparatus, you actually get more discrimination. So frictional differences are actually enhanced by the presence of fingerprints, at least for these artificial silicone mock-ups of fingers. Another scenario that we were interested in is softness. So how is softness quantifiable in terms of human perception? So softness, we picked softness as opposed to hardness because hardness has an engineering definition, like the Brinell test or the Vickers test, whereas softness, okay, it's like the inverse of hardness, but there's not really a definition of softness. But there's still an idea that something that has a large indentation depth and large spreading contact area is between a hard indenter and the surface is something that's going to be soft. The problem is that most commercial materials, if you go to the hardware store and you buy a silicone slab, you buy some harder silicone slab, the contact area and the indentation depth will actually scale together. So we need to decouple these parameters. So Charles did this work recently where he tried to decouple these parameters by changing the contact area or manipulating it by changing the exposed surface area using soft lithography, and also changed the indentation depth independent of or not independent, but in addition to manipulating the modulus, you can change the stiffness and indentation depth by changing the thickness. So if you make something really thin, even if it's a very soft material, it won't indent very far because it's confined against the bottom surface. So, so Charles made 9 slabs which varied in 3 different parameters, and you have to memorize this whole table. Just kidding. They're kind of differentiated by these markers here, and I'll show you, and kind of the shape here. 3 stands for 30%, 5 points stands for 50%, circles are 100%, and so on. But I'll try to describe to you what I mean as we go. The modulus itself was jumbled because we didn't want to prove the trivial result that the higher the modulus, the harder it is, because duh, right? So, so this is one psychophysical test that we did where we had, it's like an eyeglass test, like better 1, better 2, better 1, better 2, better A, better C, better 3, better 4. And I swear that half the time the eye doctor is actually using the same ones and then calling them different things just to psych you out and make sure that you get the right prescription. But anyway, so it was like softer 1, softer 2, softer 1, softer 2. And the participants, and this is a plot of the participants' aggregate percentage for each one judged softer. So this one judged soft most of the time, this one judged soft not very much. You can plot these data in a different way if the experimenter keeps track of which ones are actually involved in the comparisons. So this is a plot of the paired comparisons where we have these. This box corresponds to like light blue interacting with red. And you can see that the redder it is, the more likely it is to be judged soft. Okay, so this kind of looks like it is meant to be symmetric. What's interesting here is that the axes have the slabs in the same order. That's actually profound. And why is that profound? Because it's possible in paired comparisons to have outliers where, for example, suppose you are doing not softness of silicone slabs, but the quality of a classical composer, and you have Beethoven and Mozart. Suppose Mozart wins most of the time. Mozart better than Chopin, better than Debussy, whatever. But then Beethoven, who loses a lot. But once Beethoven is up against Mozart, Beethoven beats Mozart most of the time because of some kind of psychological comparison that people are making. So it's not guaranteed that the aggregate percentage and the paired comparisons would actually line up. So the reason, why it lines up is important because that shows us that there's transitivity to the perception of softness. That softness, at least as our participants were defining it to themselves, exists on a one-dimensional axis. So this plot is a plot of perceived softness versus the thickness, effective surface area, and modulus, and you can see there's basically no correlation. If you look at indentation depth, there's actually slightly more correlation. Contact area maybe slightly more, but still pretty bad. So we know that there has to be some combination of these properties that give you the perception of softness. Now, this is a type of analysis called an Ike information criterion that I had never heard of before I started doing this work, or mentoring Charles while he did this work. But basically what this does is compare different models of modified Hertzian contact to the psychophysical data to try to predict which combination is the best. And it turns out that the contact area plus the square root of the indentation depth is a model with the appropriate coefficients that most accurately predicts which material is going to feel softer than another. So the ultimate goal is to be able to make a material that can change its contact area and indentation depth in real time to have a surface that can change its perceived softness in real time. So we're working on that now using a few different approaches. Now, just to tie up some loose ends, the features, the topographic features are very small. They have like a pitch of 40 microns. And the 2-point discrimination that human skin has is more like 1.7 millimeters or something. So we're not feeling the individual features. So how is it actually affecting our perception of softness? One hypothesis, and this at least got past the reviewers when they asked, is that it actually changes the strain field within the near surface of the finger when you have a topographic surface versus a planar surface. So the conclusions here are that softness is not dependent on intrinsic properties of materials, but rather how the finger and the surface interact. Porous surfaces generally feel harder, all else things being equal. Softness is a transitive property. Also, we learned that humans tend to ignore the deformability of their own finger, and the contact area is determined by the overall integrated contact area as opposed to the projected contact area. There's Charles' picture again. Okay, I'm almost done. I know I'm over time, but I'm almost done. All right, so we used the glass transition temperature. So Charles' project is really about the near surface softness. So like, is skin soft? Is like the softness of a baby skin or something, but not the bulk softness, not like the bulk modulus. Like if you squeeze like a balloon or something, how soft is that? And to mimic those sensations, we need a way of interacting with the kinesthetic sense, not just the tactile sense. The kinesthetic sense is the sense of motion and forces. So Cody had this idea to take a thermoplastic, an acrylic thermoplastic, and embed it in a spandex glove, and attach thermoelectric devices into it to reversibly freeze and thaw this glove at a temperature range which is barely detectable by the participant wearing the glove. So this is where we hooked it up to a robot finger. Robot finger is a pressure sensor. When the robot finger meets this wall, it says there's an obstruction here, sends a signal to the thermoelectric device to cool down, and the finger becomes stiff. It turns out, so our reaction times, by the way, are not very good because this is a thermal process, but anyway, it's the first time that someone's done this, so hopefully we'll get this down from like 20 seconds to like much better than that. But anyway, what you can kind of do if you get overzealous with this device and you kind of like crunch it, like so that if it's in its glassy state, you squeeze your hand and you break the polymer. Because we're just exploiting the TG here, you can actually just put it back in your easy bake oven for a few minutes, and it will reheal itself. So we're interested in materials that will change their properties in real time, and to kind of bring this back to conjugated polymers, then I'll be done. Is we're interested in making a new form of a conductive polymer that could be soft, skin conformable, and also actuated using electric potentials to drive a tactile sensation. In this case, to mimic roughness. So there's an effect called the electrotactile effect, which has the ability to depolarize the nerve endings responsible for mechanosensation in your fingers, so that it's possible to mimic a variety of feelings. This is done by work done by Laura Kaiser, who's now a professor also in the MSc department at U Delaware. You can see that this material she made is very tough and has lots of extensibility. If you incorporate it into this glove, this work was done primarily by Colin Keefe, who is a master's student in ECE. It's possible to add electrotactile functionality, vibrotactile functionality, and thermoelectric devices to actually feel what robot hands are feeling to some extent. Trust me that this person can actually feel something. Eventually you'll have like Aldous Huxley's Brave New World feelies at the chair, so you can like feel what's on the presentation screen. So yeah, it also works. So the temperature, this is a heat gun, and then I'm actually wearing the glove in this case off screen, but trust me that it is getting hot. All right, there's Colin's picture, and so this is me testing out the device in virtual reality. So these are 8 unknown slabs of material that differ on the basis of roughness, which is done using the conductive polymer. So roughness, the idea was, so you change the intermittency of the electrotactile signal to kind of simulate bumps on the surface. So it goes like for smooth and then for rough. Kind of feels like it. And then hardness and softness was done using a commercial vibrotactile actuator. So so basically the frequency of the vibration was like how hard the restoring force was, and then temperature was done using a commercial thermoelectric device. So human subjects, if you tell them what to expect, they're very good at determining the differences between these characteristics. If you don't tell them, they're actually still pretty good. Some of these are within error, but in a real situation, like if you had these devices that could actually mimic like turning a breech baby or feeling like a fibrosis in a swallowing muscle, and you could actually come up with the right materials, of course that person would be trained. So I'm more encouraged by the left column than the right column here. Okay, hopefully I've convinced you that there's something about conjugated polymers and electromechanical behavior and soft and things kind of tied together and make it all make sense that this is all happening in one research group. So sometimes if there are disparate projects, people like to have a Venn diagram, but I'm a child of the 80s, so I like the Triforce of power, and that is the mechanical properties of electronic polymers, and then using these types of interactions and nanostructured thin films, you can make a variety of sensors, and you can make haptic biomaterials as well. So with that, I would like to give credit to my group. These people on the right are recent additions to the group, so not in the group photo. Support from these institutions and foundations. I'd especially like to acknowledge this grant from CBET, which has recently started funding our work in haptics, and also our outreach efforts on YouTube as well, which you're welcome to check out. So thank you very much for your attention.